Hey everyone. So today we are going to continue with data visualizations. In the last class, we covered two graphs. One was the scatter plot and the other was pair plot. We also discussed the difference between matplotlib and seaborn. So both are data visualization libraries, but matplotlib is used to make basic graphs, whereas seaborn is an advanced version of matplotlib. Now, let's see. Matplotlib versus seaborn. So here we have basic graphs, right? And here we have advanced graphs, and it's an advanced version of Matplotlib. In Matplotlib, we have complex and lengthy syntax, whereas in Seaborn, we have comparatively simple syntax. Okay, that's the main difference between Matplotlib and Seaborn. And Seaborn is an extended version of Matplotlib, which uses Matplotlib along with NumPy and Pandas for plotting graphs. Okay, now we discussed two plots. One was the scatter plot. So in scatter plot, what do we do is we have one feature on the x-axis and one feature on the y-axis, and each point is represented by a dot. Right? This is the scatter plot. And what is pair plot? Pair plots are basically multiple scatter plots drawn together for all pair of continuous variables. So that was pair. Now we are going to continue with other plots. So let's start off with the next, which is called as box plot. Now, for box plot, we need to understand a few things. We already know what percentiles is, right? And we also discussed what Q1, Q2, and Q3 mean. So Q1 is the 25th percentile, Q2 is the 50th percentile, which is also called as the median, and Q3 is the 75th percentile. So what is box plot? Box plot basically represents Q1, Q2, Q3, and with that it represents other two measures also, which is the minimum and the maximum. So basically min value of the column plus Q1 plus Q2 plus Q3 plus max value of the column. All these five together are called 5-number summary. So what is the 5-number summary? The minimum, 25th percentile, 50th percentile, 75th percentile, and the max value. They all together are called 5-number summary. Basically, these 5 numbers, they describe the data. Now, these are used to make the box plot as well. So if you see, you make a box, let's say your min is 6, Q1 is, let's say, 7, Q2 is, let's say, 9, and Q3 is 11 or 12. And max is 50. So how do you draw the box plot? You draw the box plot of if let's say this is the number line, you can have number line in any way, either on the horizontal or on the vertical. Let's have it on vertical. Okay. So your min is 6. Okay. First, let's draw a box. So we draw a box between Q1 and Q3. So 7 is here, 12 is here, right? So we draw a box like this. Like this. So we draw a box between Q1 and Q3. And then we draw Q2 also in between. So here we have 7, here we have 12. Then we have 9 also. 9 will be somewhere here. So we draw Q2 like this. So basically we have a box between Q1 and Q3, and then we also draw Q2 in between wherever it is. Q2 will not be exactly in the middle of Q1 and Q3, but it will be somewhere between Q1 and Q3, not exactly in the middle. It can be exactly in the middle, it cannot be exactly in the middle. So it's just that Q2 will be between Q1 and Q3. So we just draw a line like this. Basically, if we have it in this way, then we just draw a line. Okay, for Q2. So right now, how does that box plot look like? like this. Let me draw proper lines like this. Okay. And then our minimum is where? Minimum is at 6. So at 6, we draw like this. So what we have is basically a small line that we draw, and then we connect the box and the line. And similarly, the max is at 15. So a small line like this, and then we connect it with a rectangle. So this essentially is your box plot. So here is your 6, here is your 7, here is your 9, here is your 12, and here is your 15. So this is basically the box plot, and we can draw box plots for any column, right? So let's draw it using Seaborn. So SNS dot, we have to call box plot. So for that we'll have box plot. Exactly. Let me do control space and let me see if I get some suggestions. Yes, I get the suggestion box plot. And in that, first you have to give y. Y is basically the column that you want the box plot for. So let's say we want it for the 10th percentage. And the data is basically the data frame that you are going to use. So we have df. So if you see, now you will get the box plot. Okay. So this is the box plot. This will be the minimum. This will be the Q1, Q2, Q3, and the max. Now let's draw the box plot for 12th percentage also. So how do we draw the box plot for the 12th percentage? We draw it using SNS dot box plot, and we were writing, if you see, okay, we were writing the questions, draw the pair plots. So let's write the questions also, basically what we are doing with the text. So this is the text cell, draw box plot for 10th percentage of the students. And then again a text cell after this, draw a box plot for 12th percentage of the students. So we have SNS dot box plot, and here we have to provide y, which is going to be our column, that's the 12th percentage, and the data that we have to provide is df. So now if you see, you see some things like these. What are these? Obviously, this is the min, this is the Q1, Q2, Q3, and max. But what are these exactly? These are actually the outliers. These are the outliers. Outliers are removed. They are not included in the min or the max, and they are just separate. So if you see in the box plot, you see the outliers also. Now, how do we get the outliers? Okay. So first step is you figure out Q1, Q2, and Q3. And then Q3 minus Q1, that is the 75th percentile, minus the 25th percentile is basically called as the interquartile range. So basically the max minus min, this thing is called the range, and Q3 minus Q1 is called the interquartile range. Okay, Q3 minus Q1 is called the interquartile range. So basically, let's say this is Q1, this is Q3, and here we have Q2. So you find 1.5 times after Q3. That is, you move 1.5 times IQR, 1.5 times interquartile range from the to the right of Q3, and you move 1.5 times IQR interquartile range to the right to the left of Q1. So basically, this is the boundary. Any point outside of this will be an outlier. So basically you take 1.5 times interquartile range to the right of Q3 and 1.5 times interquartile range to the left of Q1. And any point to the right of this or to the left of this boundary, These are the boundaries, and any point to the right of this boundary or to the left of this boundary will be a outlier. So any point, if x is greater than q3 plus 1.5 times IQR, will be an outlier. That is, if any point is here, it will be an outlier. And any point which is, since we are going to the left, so we have to subtract. So any point to the left of q1, and it's to the left of q1, but it's ahead of 1.5 times IQR. It's basically after this boundary. So if any point is less than q1 minus 1.5 times IQR, that is the point is here, then also it is a outlier. So these are the two conditions that we have for outliers. Okay, so let me write it. So if any point it's greater than q3 plus 1.5 times IQR, it is basically a outlier, and if x is less than q1 minus 1.5 times IQR, it is a outlier. So these are the two conditions for outliers. So in this way you are able to see the outliers here and here. Okay. So now, in the pre-processing, once we complete the visualization in the pre-processing, we will see how do we remove the outliers also. We'll follow the same concept. That is, if the point is greater than Q3 plus 1.5 times IQR, it's a outlier and it has to be removed. Similarly, any point which is less than Q1 minus 1.5 times IQR, it's an outlier and it has to be removed. Okay. Now we understand what line plots are. So in line plots, what happens is, on the x-axis, we have the index, and on the y-axis, we have the column or the list that we provide. So let me say I have a list y. Just to understand line plots, let's create a list 1, 2, 5, 2, 1, something like this. Okay, and then we are going to use matplotlib.pyplot as PLT and then call PLT dot. Just do the plot. So basically, plot is giving you the line plot, and here you provide your y. So basically, these points will be on the y-axis, and on the x-axis, we are going to have the index. So basically, at the 0th index, we have 1. So that's the point here. Then at the first index, we have 2. So the next point is here. Then at the second index, we have 5. So that's why we have the point here. Then at the third index, we have again 2. So it's here. And at the fourth index, we have 1. So again, this is basically the line plot. So basically on the y-axis, we are going to have all these points and on the x-axis, we'll have corresponding indices. So index 0, index 1, index 2, index 3, index 4. Let me just change it to 6. So basically your line plot will change. Now, basically at the fourth index, we have 6. So basically here, what's the criteria? The criteria is that the line plot depends on the values that you provide, the order of the values that you provide. Okay, so if let's say 6 is here, then your line plot will change. So for this, the line plot is like this, and if you change the order, if you just change the order of the points, the line plot would vary. Okay, so here it is basically plotting the points versus their indices. Now, these graphs are not generally useful in these type of data sets, but they are useful when we have some time series data set. That is, on the x-axis, we have time, and then basically we are seeing how let's say the temperature or the stock price is varying with time. So if on the x-axis we have temperature, and here we have, let's say, if on the x-axis we have time, and on the y-axis we have temperature. So basically, then if we see how the temperature is varying with time. So in that case, these line plots are helpful. But for these data sets, they are not so helpful. But let's draw, and we can also provide the label. So we don't know what this blue line is, right? So we can provide the label, that is points So we'll get the label as well. But the label won't appear on its own. We'll have to say plt dot legend like this. Then only the label will appear. Okay, so you can write the label, but you'll have to say that hey, print the hey, show the legend. So then only our label is going to appear. So let's now take the question. Draw the line plot for 10th and 12th percentage in the same graph. Okay, so now how do we do this? We'll say plt dot plot, and we are going to have the column SSCP, which is the 10th percentage, and here again we'll say plt dot plot in the same graph, since we want the 12th percentage also. Okay, we get both the graphs, but I don't know which color is 10th and which color is 12th. Blue can be 10th percentage also, and it can be 12th percentage also. So I should give the labels. The labels should be provided here. 10th percentage. And here label 12th percentage. But if you don't say the legend, it's not going to appear. So you will have to say plt.legend. So now you will have the labels appearing. So you see this is the legend which has the labels. So blue is the 10th percentage and orange is the 12th percentage. So this is useful when on the x-axis you have something very useful like time, or how the temperature is varying with something. But here it's basically the index, which is not so very useful. Okay. Okay. Now let's go to heat map. So heat map basically is a method of graphically representing numerical data where value of each data point is indicated using colors. Okay, let's see with an example. So first of all, let's see a use case of heat map. Find correlation between all continuous columns. So if you do df.corr, this is something that we already discussed, we'll get the correlation matrix, right? So you see we have the correlation matrix. Let's draw the heat map of the correlation. So draw heat map of the correlation matrix. Now, heat map is basically a method of graphically representing this matrix in form of a matrix where we just have colors. That is, each of these numbers will be indicated by colors. So we'll have a matrix of colors, essentially. So how do we create a heat map? It's simple by Seaborn. So you just say SNS dot heat. You can just do a control space to get the suggestions, and we have heat map. And here we want to create the heat map for the correlation matrix. So if you see this, so here also it's a matrix. Here also it's a matrix, but it's a matrix of colors. So basically, SSCP versus SSCP correlation is 1. Obviously, correlation of an attribute with itself will be 1. So if you see SSCP versus SSCP is this color. And what does this color? This is a cream color, which is 1. Then if you see SSCP versus HSCP, here it is 0.511472. Here you see it's this pink color. So you have to figure out where this pink color is. It's somewhere here. So based on that, uh, you'll get the value. Now, why do we do this? Because obviously, seeing this data in tabular format might not be very appealing to us. We might not understand a lot from here, but we can understand a lot from the colors when we see the difference in colors. So basically, the dark colors means that there is less correlation, that is very less correlation. And if we see some light colors here, it means that there is high correlation. Now, obviously, you would find this very difficult because there are a lot of colors and you have to find it out in the scale what the color is. But this would make much more sense if I write the correlation on top of each cell. I can do that. So annote, I just have to say the annote, that is the annotation should be true. That is, you're going to put colors on top of these cells. Now this would make much more sense. Now it would be very easy for you to figure out. Obviously, you know dark colors means less correlation, light colors means that there is high correlation, and now you can easily understand this. So obviously, this heat map is better than this tabular format. So heat map is basically a method of graphically representing numerical data where the value of each data point is indicated using colors. Okay, that's the heat map. So we've done how many plots? We have done scatter plots. We have done pair plots. Then we have done line plots, box plots, and heat map. These are the 5 graphs that we've already covered. Now, let's draw histogram. So first of all, we discussed histogram in brief when we were discussing the pair plots, but let's understand histograms for now. So let's say we have the data like this. 72, 83, 85, 87, 99, 100. So basically, here we have these data points available with us, and I want to have 10 equal intervals. Basically, I want to split this data into 10 equal intervals. So basically, the min is 0 and the max is 10. Okay. So basically, if I want 10 intervals, so basically I have max minus min, which is 100, and I want to split it into 10 intervals. So basically, each interval will have what? It will have 10. 10 would be the width of each interval, right? So basically, I will have intervals starting from 0 to 10. Then I will have 10 to 20. Then I will have 20 to 30. Then I will have 30 to 40. Then I will have 40 to 50. Then I will have 50 to 60. Then I will have 60 to 70. Then 70 to 80, then 80 to 90, and then 90 to 100, right? Let's remove this point for now because otherwise we would need 100 also. So basically what we are doing is we are dividing the data into, we are dividing 10 equal intervals. We have 10 equal intervals here. So if you see how many points are there in this interval, in this interval 0 to 10, there is just 1 point. In this 10 to 20, how many points are there? 4 points. And in this 20 to 30, there is just 1 point. Then from 30 to 40, how many points are there? If you see, there's only 33, that is, there's 1 point. So basically in histogram, what do we do is, on the x-axis, we have the interval. So first interval would be 0 to 10, then the next would be 10 to 20, then the next would be 20 to 30, and so on. And on the y-axis, we basically will have the frequency. That is how many points belong to each interval. Let me draw a line here. Okay, 1 second. Okay, so basically 0 to 10, how many points are there? There's 1 point. So basically 1 is here. So we draw a rectangle like this. So basically we will have rectangles, and the length of or the height of the rectangles will denote the frequency. So basically 0 to 10 has 1 point. Then 10 to 20 has how many points? 2, 3, 4. So 10 to 20 will have 4 points. So we draw interval, a rectangle like this. Then 20 to 30 will again have 1 point. So we draw a rectangle like this. So this is basically a histogram. So what do we do is we have intervals, and basically on the y-axis we have number of points which belong to that interval. We draw rectangles with the height equals to number of points belonging to that equal interval. That is basically the frequency. So basically frequency means the number of points which are in this interval. So the frequency of the interval 0 to 10 is 1. That is the number of points which belong to that interval. And each rectangle, the length of each rectangle denotes the frequency of the interval. Okay. Now, let's draw the histogram. So let's draw the histogram for salary. Draw the histogram for salary of students. So what do we do is we can just use the matplotlib histogram function, which is hist, and just provide the column salary. So now if you will see, you'll have the salary. So basically in the first rectangle, that is from 0 to something, we have around 67 students, right? And then in the next interval, there are no students. In the next interval, there are many students. In the next interval, there are less students, and so on. Okay. Now here, if you have to figure out something, we figure out that majority of the people, they have their income who are placed. Obviously, the unplaced students are having zero, right? For the placed students, we see that their income is like for most of them is in the range 2 lakhs to 2 to 3 lakhs. Okay, so in this range, most of them lie, and there are only a few students whose salary is greater than 8 lakhs. So that's what we can figure out from the histogram. Okay, when we were discussing the histogram, we also discussed something called as KDE. KDE, that is the kernel density estimate. It is the approximate distribution. It is the approximate distribution of a column. Or let's say if the KDE looks like this, so this is the approximate distribution from which the column or the variable is coming from. So let's try to draw the KDE for the, let's say, 10th grade, 10th grade percentage. So draw the distribution of 10th grade percentage. So we basically have SNS, and then we draw the KDE plot. Okay, and for KDE plot, we just have to write KDE plot and then just provide the column. So let's say SSCP. So basically, this is going to tell us the approximate distribution from which our 10th percentage would have come from. We can draw the KDE for the salary also. Draw the KDE, or the distribution, approximate distribution of salary. Let me delete this cell. So we have df dot KDE plot, and we provide the salary. So this is the column that we provide. Now, okay, it's not df, it is SNS, right? So if you see, it is coming from this distribution. So we are done with most of the graphs. So we started off with scatter plots, then we went to pair plots, then we went to box plots, then line plots, then heat map, histograms, and then KT. So these are the basic graphs that are used to do the data visualization. And data exploration has two parts. One is the summary statistics or the descriptive measures, and the second one is data visualization. Okay. Now we will start off with the pre-processing again, the initial pre-processing that we did. was just removing the null values. Did we do anything else? Let's see. So basically this has everything that we did in the previous class also. So we just removed the null values. That's it. We did not do anything else. Okay. So now we are going to start off with data preprocessing again. So let me write the heading, data preprocessing. Why did we remove null values before? So that it does not so that we have the complete data and then we can do the visualizations. Otherwise missing values would have been a problem. So that's why we just filled the missing values. Now the first thing let's do here is outlier analysis. Let's put it in bold. Outlier analysis. Okay. Now, what do we do in outlier analysis? So basically we check for each column. We check for each column and we figure out the Q1, the Q2, Q3. And we only take those points which basically are inside the boundary. What's the boundary? Let me draw it. So this is Q1, this is Q2, this is Q3, this is 1.5 times IQR to the right of Q3, and this is 1.5 times IQR to the left of Q1. We are only going to take the points which are within this boundary. Any point which is outside, we don't have to take it. And this is the same concept that we are going to use for all the columns. Okay, let's see. So first let's print the DF. Okay, now the next thing that we do is first let's just take one of the columns. The columns is, let's say, degree P. Let's take degree P. Okay. So let's draw the box plot for it. So SNS dot box plot, and we provide the column name, which is degree P, and then we have to provide the data. Okay. Also, you can directly write SNS dot box plot, and you just have your degree P. Just instead of y is equals to, you just write degree P, and you write DF. So now it gives the error could not interpret input degree P. So if you have to check it again, you will have to write. So basically you cannot just provide degree P and DF. You will have to explicitly define what is Y, what is data. Y is basically the column name, data is the data frame that for which you are taking the column name. If you just write degree, will it give an error? Yes, it will give an error because degree is not a column name. So you have to provide the column name, which should be a column name in this DF. So you have to write Y and data. You cannot go without it. Okay. Now, if you see, we have an outlier here. So let's try to remove the outliers. Let's basically first figure out the 25th percentile. How do we figure out the 25th percentile? So basically you take degree P, you have something called as mean, mode, all these functions are there. So similarly, we have a function which is called quantile. And basically, since we want the 25th percentile, we will have to provide 25 by 100, which is 0.25 here. And this is going to give us the 25th percentile. So to get the 25th percentile, we have a function called quantile. And let's store this 61. If you see, 61. This 61 is the 25th percentile for us. And let's store it in a variable which is called percentile 25. Okay. Then let's figure out the 75th percentile. And we again provide quantile, and since we have to figure out the 75th percentile, the value that needs to be provided here is 0.75. So this is the 75th percentile. So if you see, Q3 is somewhere near 72. So this is basically percentile 75. Okay. Now what we want? We want the interquartile range, which is percentile this thing minus this thing. So basically it's percentile 75 minus percentile 25. Percentile n is missing. Now this is basically our percentile. So this was 61 and this was 72. So 72 minus 61, it's 11. So now this is our interquartile range. Let me call it as IQR. Okay, these are the variables that I'm defining. Now let's figure out the upper limit and the lower limit. So what is the upper limit? It is basically 75th percentile, which is percentile 75 plus 1.5 times of IQR. This would work, but let me just put braces also for readability. So this is the upper limit that I have. Let me store it in upper limit variable. Okay. Now, similarly, we want the lower limit, which is percentile 25 minus 1.5 times of IQR. So this is going to be the lower limit. Now I have to take only those points, only and only those points which are essentially in between the upper limit and the lower limit. So basically, you take degree P and you check if the value is less than the upper limit. If it is, then you have to take that, and you have to also check. And how do we check the condition? Is it bitwise, and like how do we do it, or is this like this? What do you think? Let's try with this. And it should be greater than the lower limit. So basically, we are only going to take the points if they are less than the upper limit, less than equals to the upper limit, equal to will also work, and greater than equals to the lower limit. So the truth value of a series is ambiguous. What should we do? Obviously, first put the braces. It still gives the truth value of a series is ambiguous. Should we use a bitwise AND? Yes, we have to use a bitwise AND like this, not that AND. So you have to use a bitwise AND. And always for readability, try to put the parenthesis. Okay. So now if you see, let's see this. Let's see this as well. So if you see, true and true will give a true. That's why we are getting true here. But there would be some points. Obviously, there is going to be only one point. If you see, there's only going to be one point which does not follow this criteria. So now we have to take all those points which give a true. So basically, we have to take DF of this. So we have to take all the records which give a true. And let's see how many are there. There are 204 rows. Initially, how many rows were there? There were 215 rows. But now that outlier point has been removed. So we are basically removing that outlier. Okay. So now you can just say that this is going to be a new DF. Like this. So now if you see, your DF is going to have to 1 4 rows. Now it depends, like it depends on you. You want to remove the outliers for all the columns, or if you want to remove outliers for some columns, or you only want to remove outliers for the target column. It depends on you, but it's a good practice that you remove outliers. Okay. Now we followed this process, the entire process for degree P. So basically, we only took those points which were in the boundary that we set, the upper limit and the lower limit. If the points were inside it, then we are good. Otherwise, we are not going to consider those points. So we can do it for all the continuous columns. Can we do it in a loop? Yes, we can do it in a loop, and that's what we're going to do. We can do it in a function also, and we can call the function for all the columns. But let's do it in the loop format. So we have already done it for degree P. What are the columns that are remaining? Let's create a list of the columns that are remaining. We have SSCP. Then the next column that we have is HSCP. Basically, all the continuous variables we are taking. Then we have degree P. Then we have e-test P. Then after that we have MBA P. And after that we have salary. So these are the columns. For degree P we are already done, right? We don't need to do it again. So we can remove degree P. So these are the columns for which we want to do the outlier analysis. Okay. Also, let me just show you, we have the DF, right? Let me just show you the box plot again. So that we see that there is no outlier. DF dot, sorry, SNS dot box plot. We provide SSCP, sorry, degree P, and data is equals to DF. Can we see the outlier? No, the outlier has been removed. So if you see this, we had outlier, right? We had outlier, but now the outlier has been removed. Do you see that? Now if you see here, yes. Okay, the outlier has been removed. Now, so what we'll do is for all the columns, for C in columns, for all the columns, we are going to do this. First, we'll plot the box plot. So SNS dot box plot. But if we do this, will we get, so Y should be equals to the C, that is the column name, and then data has to be TF, right? So basically for each C, that is for SSCP, for HSCP, for ETSP, for MBAP and salary, this is going to be executed. But will we get all the graphs? No, we won't get all the graphs. We will just get the last graph. Why does this happen? This happens because the same graph is being overridden. First, you drew the graph for SSCP, then you overrode it with the graph of HSCP, then you overrode it with ETSP graph, then you overrode it with MBAP graph, and then you overrode it with salary graph. So finally, the salary graph is only available to you. But if you write PLT dot figure, that is, you basically create a new figure and then draw the box plot. So in this way, what happens is first you draw a figure, you draw a plain figure blank, and then you draw the box plot in it. Then again you draw a new figure and then put the second box plot in it. Then you draw the new figure and then put the box plot. So if you see, HSCP has outliers and salary has outliers. Others don't have outliers, right? So you can just do the outlier analysis for these columns because others don't have outliers. SSCP does not have, HSCP has, and then only salary has. So basically, you can now have your refined column list, which is HSCP and salary, right? You don't need to do it for all the columns. If you do it for all the columns, that's also fine. But since it's not needed, we are not doing it. For C in column, now we'll do the outlier analysis. So first, what do we do? Let's create a blank figure and draw the box plot. So SNS dot box plot. Y is going to be either HSC, first it will be HSCP, then it will be salary. So Y is going to be C and the data is going to be DF. So let's do this. So we'll see that there are outliers in HSCP and salary both. So first, what should we do? We should find the 25th percentile. So percentile 25 is equals to, you take the column. So in the first iteration, you take HSCP. In the second one, you take salary. So since we have C as the variable, we are going to write DFC. Okay, that we take the column. First, C will take the value HSCP, and then second, it will take the value salary. Okay, so here you have to find the 25th 25th percentile, which is basically in quantile function, right? 0.25. Then you write percentile 75 to calculate the 75th percentile, and in the quantile function you give 0.75. Then you find out the IQR, which is interquartile range, which is percentile 75 minus percentile 25. Okay, hope we are not doing anything wrong. Percentile 25, quantile, percentile 75, quantile, percentile 75 minus percentile 25. Okay, now we'll figure out the upper limit. So upper limit would be percentile 75 plus 1.5 times IQR, and lower limit is percentile 25 minus 1.5 times IQR. Okay, and then we have to take only those records where the value of the column is less than equals to the upper limit and greater than equals to the lower limit. So this will give us true or false. So we have to take only the records which give true and then update our TF. And then we can again draw the plots and see if there are outliers. PLT.figure. So after the two figures that we have here, after that another two figures will be created with the removal of the outliers, and we shouldn't see any outliers further. So SNS.boxplot, then you write Y is equals to C, data is equals to DF. Hopefully we have not done anything wrong. So first you see the first graph, we have HSCP, then we do the outlier analysis for it, and then we don't see any outliers. So the outliers are removed. Then we have salary, and for that we have outliers, and then we do the outlier analysis for it, and it's removed. So this is basically how we do the outlier analysis. You can do it for all the columns also, that is these columns, but it's just that we figured out that we don't have outliers in some of the columns. Then why do we need to do those iterations? If let's say you have a very big data set, then probably doing those computations is going to take time and space. So those computations can be removed. Okay, now let's encode the categorical variables that we have using one of the encoding techniques. Maybe let's use label encoder. So let me write the next one as label encoding. Okay, so let's first see our DF. Now, obviously, some of the records have been removed because we did the outlier analysis for degree P, HSCP, and our salary. So basically, we have 205 records left and we have 14 columns. But if you see, we have gender as male and female, SSCB as others and central. So basically, these object data type columns, they cannot be understood by our machines, our models. So we have to convert them, we have to encode them. And we encode these categorical variables. Either we can do one-hot encoding or we can do label encoding. And we'll do label encoding now. Okay. So now we have something called as another Python library, sklearn. So sklearn is the another library. So far we've used NumPy, we've used pandas, we've used matplotlib, and we've used seaborn as well. Now, what is this sklearn, or it's also called scikit-learn? It is most useful and robust library for machine learning in Python. It provides a selection of efficient tools for machine learning and statistical modeling. So it's going to provide you pre-processing techniques, it's going to provide you classification, regression, clustering, dimensionality reduction models. It's going to provide you lots and lots of models. So this library, which is largely written in Python, is built upon NumPy and Matplotlib, right? So this is the library which is going to help you invoke lot of models and just write models in 3 or 4 lines, or even do data pre-processing in 3 or 4 lines. So you don't have to write the explicit code for each and everything. We can just invoke this library. So it's basically a library which provides us efficient tools for machine learning and statistical modeling. So how do we do label encoding? So basically, we have to invoke label encoder, and that label encoder is present in sklearn.preprocessing. So sklearn has a lot of things. So we have to invoke sklearn.preprocessing. So from sklearn.preprocessing, something like we were doing matplotlib.pyplot, right? So sklearn has a lot of things. It has pre-processing, it has linear models, it has trees, ensemble. So there are lots and lots of categories. So we have to invoke pre-processing from there for label encoder. So from sklearn.preprocessing, we have to import label encoder. Let me just do a control space and I get label encoder. And this is basically how we are going to import label encoder. And the second step would be to instantiate an object of label encoder. How do we do that? Like this. This is how we instantiate an object of label encoder. And let me call it as LE. Okay. So if let's say we have to do the label encoding for maybe SSCB, then what you have to do is, so first what will happen is there are two functions of LE or the label encoder. The first function is fit. Fit function basically finds out which attribute value should be given what number. So basically we have others and central. So central should essentially be given 1 and others should be central should be given 0 and others should be given 1 based on the alphabetical order, because central comes before others, right? So central is 0 and others is 1. Now fit function is going to figure out which attribute value should be given what numerical value. So which attribute value should be given what numerical value, and the transform function actually does this transformation. It replaces the others and central with the zeros and ones. So for example, if we had OCOCO, so fit function will figure out, hey, there are two unique values. So C should be given the value 0 and O should be given the value 1. Let me write OT so that things are clear and we don't confuse between others and 0. Okay. So the fit function is going to give C value 0 and others the value 1. And this is only the thing that fit method will do. Transform function will actually do the conversion. It will see that OT should be given the value 1. So instead of OT, it's going to write 1. Instead of C, it's going to write 0. OT again, so 1. C, 0. OT, 1. So basically, fit function is just going to tell which attribute value should get what number, and transform will actually do the conversion. We can call fit transform both together, and that function name is called fit underscore transform. So we can call that directly. So le dot fit transform, and we basically have to just provide the column, which is what was that? SSCB. So now you will see that our other central, all this is converted into ones and zeros. Since there is only others and central, those two unique values are only there. So others get the value 1, central gets the value 0. So first we had others written, right? So it should be 1 0 0 0 0. So if you see, it's starting from 1 0 0 0 0, right? So now what you should do is you should actually have this instead of SSCB. So if you see your SSCB, it now has central, others, and so on, right? What we should do is we should just say that our DF of SSCB should be equals to this. Basically, it should be converted into the ones and zeros. So basically, this array, whatever the values are, it will basically be put in SSCB. So now if you see your SSCB, it will have the ones and the zeros, right? Does that make sense? Yes. Now we have the ones and the zeros. So now we can do this for all the categorical variables. Okay, we can do this for all the categorical variables. Let's see which are the categorical variables. The categorical variables we have as gender, HSCB, SSCB we've already done. Then we have HSCS, then we have the degree T, then we have workx, specialization, and status, right? Not place will get 0, place will get 1. So let's see all these columns. Let me first do df.head and just take one of them, the first record, and we are going to see column. Then we will have the columns that we need. The first one is gender. We have already handled SSCB, so now we need HSCP. Then we have HSCB. Then we have, okay, we don't need HSCP. HSCP is basically number, right? So we don't need that. We need only the categorical variables. So now we need HSCS, then we need degree T, then we need workx, then we need special, let me just copy it from here, specialization, and then we need status, right? So gender, HSCP, HSCB, HSCS, DVT, workx, specialization, and status. So these are the columns that we need. And now we can do it in a for loop. For C in columns, what should we do? We have to update the column with the fit transform. So le.fit transform So basically, we do the fit transform for all the columns. That is, we do the encoding and then replace the encodings that we get with the column. So basically, instead of these all attribute values or the object data type, we will have numbers. So DFC. And now if you see your DF, now we just have numbers. Why did we actually do label encoding here? Because obviously we did not have multiple or many different attribute values. We just had a few, and we did not want to add a lot of columns. Why should we increase the dimensions? Obviously, as I said, it depends when to use label encoding, when to use one hot encoding. We just used label encoding here. Okay, you could have used one hot encoding also, but here, since there are not many different attribute values. So for example, in gender, we just had 10. Similarly, in SSCB, we just had 10. In HSCB also, I think we had 10 only. Only in HSCS, we had 012, right? Here in degree T also, we just had 012. So basically, we just had 0 1s or 0 1 2. So that's why we just went for the simple one, that is label encoding. But you can also try doing one hot encoding. That's what you can do on your own. Okay. So that's it for this course, for this class. And in the next class, we are going to start off with the modelings. So thank you, everyone.